Hi folks, this is our last video applying formal logic to sets and set theory. We've already discussed the infinite size of these various sets of numbers. Despite appearances and somewhat surprisingly, the natural numbers, the odd numbers, the even numbers, the positive and negative integers, even the rational numbers all have the exact same size, namely aleph naught. What I want you to do next is consider the real numbers. So pause your videos and decide if you think the real numbers are the same size infinity as the natural numbers. Are they also aleph naught? Okay, I wanted you to think about this. The gut reaction I'm hoping for is that you think the real numbers are still the same size of infinity. After all, if even the rational numbers are dense, there's these little infinities between any two of them, then how could the real numbers not be the same size still? How could there be more than one size of infinity just by adding in a few irrational numbers like the square root of 2 and pi? Well, the amazing thing is, it turns out that there are a lot of irrational numbers, not just the ones that we give special names to or talk about all the time, like pi or the square root of 2. And in fact, the answer is no. The real numbers are not the same size as the natural numbers. This is a staggering fact. This shook the math world to its core, because what this means is that there's more than one size infinity. There's more than one infinite number. And it's mind-blowing. But the beautiful thing is, just understanding how the amount of logic that you learn in this class, you can do this proof. You can understand how this proof works. And this is really a wonderful application of logic. What we're going to do is we're going to show you quickly how this proof goes so that you can see that there's more than one size of infinity. And we're going to do it informally, because this is really the way most proofs work in mathematics journals, is informally. You can make this more rigorous if you want, but all we need is a basic understanding at this point. What I'm going to do is do it by reductio. So you already understand fully how this proof method works. What we're going to do is we're going to assume that the two sets have the same cardinality, and that's our reductio assumption. Once we prove that a contradiction results, what that means is that these are different cardinalities. Now, that doesn't yet prove which one is bigger, but at least it proves there's more than one size infinity, because they're both infinitely big. And it's quite easy to show that the reals are bigger than the natural numbers. So we'll just prove this reductio and consider our work done. The rest of it is trivial. Now, remember the concept of a one-to-one correspondence. You see, once you make a reductio assumption, like the cardinality is the same, now we just have to start making some intermediary inferences. And what follows if these are the same size? Well, that means there has to exist a one-to-one correspondence between them. That's what the concept of same size comes to, after all, when we're talking about infinite sets. Now, we don't know what the correspondence is exactly. We just know there has to be some possible correspondence. So what I've given you on this chart is just a visual understanding of what this would involve. Don't worry about these exact numbers, but there has to be something like this. We have the list of all the natural numbers, 0 and onward, and then for each one of those, we're pairing it up with some real number or other. The real numbers are interesting. They're not all expressible by fractions. So sometimes people learn in school that 22/7 is a decent approximation of pi, but that's just a rough approximation. That's not actually what the number pi is. What the real numbers are they are infinitely long decimals. And the rational numbers, the ones that can be expressed as fractions, either start repeating at a certain point, or they all terminate in the same number, like they terminate in zeros or nines or whatever. But the irrationals are interesting. They are infinitely long decimals that never start repeating and never terminate in a single decimal. So these or start repeating in a single decimal, or they never just terminate with a final digit. So these things go on forever. And what we're going to prove is that a contradiction results if we posit such a one-to-one correspondence. And that means that one of these sets has to be bigger than the other. Okay, they can't be the same size. All right, so let's start thinking, let's pursue these intermediary conclusions and think about what's involved if this is a one-to-one correspondence. Well, one thing that we know is that this list goes on forever all the way down, but every single real number has to appear on it some way or other, because any one-to-one correspondence must say exactly one of these is paired with exactly one of these, and nothing can be left off the lists. Otherwise, it wouldn't be a one-to-one correspondence. So if we can prove that there's a real number that's not on this list, then we have a contradiction, because we know there's one-to-one correspondence, but this is not a one-to-one correspondence, and this was our example. So So how could we do that? And again, this needs to be totally arbitrary. In a sense, we're doing an existential Elian proof here. And so our proof can't depend on the fact that, for example, the first real number on my list is 1, 1, 3, 4, 5, etc. I have to convince you that this proof I'm going to give you would work even if there were a different real number on this list here and a different one here. Indeed, the proof does work even if this list is totally arbitrary. Here's how it's going to go. I'm going to keep talking about this example, but again, you'll see that the particulars of the example are irrelevant. We could actually replace these with arbitrary names, basically, if you want to think about it that way. Here's the way I'm going to talk about it. I'm going to imagine a diagonal through here, and the first real number on the list, I'm going to take the first point after the decimal, and then the second real number on the list, I'm going to take its second digit after the decimal. So the tens place, the hundreds place, the thousands place, etc. And think about the diagonal that cuts through this list of real numbers. I'm going to just pick each of those digits and call it the name D. I'm going to use D as the name for whatever this is. Again, I'm giving you a particular example, but really D is arbitrary. Whatever this correspondence looks like, there's going to exist such a D. This makes perfect sense regardless of what example I choose. Now D is an infinitely long decimal string, and it might go on forever. Maybe it's irrational, who knows? Maybe it's a rational number, it doesn't matter. The thing I know is it's a real number because it's some infinitely long decimal string, whether it's rational or irrational, it's still in the set R. And also, additionally, for all I know, D might actually be on this list. This is the interesting thing. Maybe D, for example, is paired up with the number 4. Since D is just the diagonal number, it's possible that one of the real numbers on this list, in its 10th place, it has the 10th place of real number 1. In its 100th place, it has the decimal from the real number 2, etc. And of course, it intersects at the diagonal. That makes perfect sense. So this number might be on the list. Maybe it's paired with 4. Maybe it's paired with 1 million. Who knows? But D is not the problem. D might be on the list. What I'm going to do now is I'm going to use D to define a new real number. And that new real number is not going to be on the list. I'm going to call it D star, or I'll call it the counter diagonal. And this is how I make D star. I'm going to add a digit. I'm going to add 1 to each place of this decimal. So for example, D had a 1 originally, so D star has a 2. And it had an 8, and so D star gets a 9. And it had a 0, so D star gets a 3. Of course, if there's a 9 in here, then that just cycles over to a 0. So D star is a perfectly sensible number that I define on the basis of my knowledge of D. Again, if the details of D differ, then the details of D star differ, but that doesn't matter. It's not about the details. You can understand this, regardless of what this is. It's some real number, because this is going to be an infinitely long decimal string. Maybe it's rational, maybe it's irrational, who knows? But the beauty of this proof is, I'm going to try to convince you that D star cannot possibly be on this list. But remember, every real number is on this list, and D star is a real number. So we've reached a contradiction. We've proven that both there's a real number on the list, or exactly, we've proven of some real number that it's on the list and not on the list, which is impossible. That's a contradiction. So here's how it goes. Basically, we do it this way. And because remember, this is the counter diagonal. I've shifted every digit of D star somewhere. So think about wherever it could exist on the list. Maybe it's paired with 4, for example, or just call it N, whatever that is. D star, there's like, imagine that D star is on the list somewhere. This is like a mini reductio to prove to you that it's not on the list. Well, if it is on the list, there's some natural number over here that it's paired with, whatever it is. Let's just call it N. So we're in a sense considering, we're boxing in for an arbitrary constant. Well, D star cannot be the number over here, the real number paired with N, because D star differs from whatever number is paired with N in the place where N intersects, where it intersects the diagonal. Because remember, wherever any real number on this list intersects that diagonal at some point or other, namely at the N plus 1th place, basically, or the Nth plus 1 place. You know, N, the number 0 over here, intersects the diagonal at the first place. The second real number intersects it at the second place, or the number N1 intersects it at the second place, etc. So wherever this number hits the diagonal, it's going to actually be different than my D star, because D star is different in every place on the diagonal. So there can be no such n. It's impossible. D star cannot be one of the real numbers on this list, because it differs from every real number on that list in at least one decimal place, which means it's not on the list, but it's a real number, and every real number is on the list. So this is a genuine contradiction. It's impossible. So that actually finishes our big reductio. There can be no one-to-one correspondence between the natural numbers and the real numbers. This is staggering. This is absolutely an amazing reductio proof. And what you can easily prove is that, I was just looking at the real numbers between 0 and 1, by the way, in my list. But of course, there's all the other real numbers. Pi wouldn't have, real numbers 3 and greater, et cetera. So all the natural numbers are still real numbers, but of course there's real numbers that are not natural numbers. So that shows you actually why R, the cardinality of R, is greater than N, which means there's an infinite size of R, which is greater than Aleph naught. And so people use C, the real number line is called the continuum, because there's sort of a kind of, there's no gaps between the numbers in the real number line. And so we now have two infinities. The lowercase little c is used for the infinite size of the R, and C is greater than Aleph naught. It's an absolutely amazing proof. So we've used a nice reductio proof to show that there are different size infinities, and that's really cool. Let me just consider one objection before ending, because if we were doing this in a live class, there's a question that inevitably comes up. So I just want to consider it here. You see, what people often wonder is, well, what about what we learned from one-to-one correspondences from those other comparisons, like with the rational numbers and with the integers? Couldn't I just take Dstar? Maybe Dstar was not on my original list, but that's because I did a bad job constructing the original list, just like the first time I failed to get a one-to-one correspondence with the integers. So what if I try again? I'm going to put Dstar up here and shift everything down. And now this can pair all the real numbers, because I'm going to pair 0 with that one and then 1 with the next one, etc. And this should account for Dstar. Now the problem is, this doesn't actually work. The issue was not merely that this particular Dstar was not on the list, because Dstar really was totally arbitrary. The proof generalizes no matter what one-to-one correspondence I attempt to show. Excuse me. There's going to be a Dstar not on the list. It might be a different one. Like, I'll keep using Dstar to refer to the original Dstar, but now I'll use D double star to refer to the new counter diagonal. Because what I'm going to do is add 1 to each of these digits, no matter what one-to-one correspondence you give me, and you attempt to deal with some numbers at the top. There's always going to be some diagonal, and then there's going to be a counter diagonal that can't possibly be on the list. And if you think about it, there's not just one counter diagonal. There's actually going to be an infinite number of numbers not on the list, an infinite number greater than Aleph naught. You can go on and prove that too if you'd like. So there is no easy fix for this. The proof is actually rock solid and works. There are different sizes of infinities, and the size of the real numbers is greater than the natural numbers. And that's just an amazing fact. It's not just these two infinities too. If you go on to advanced logic classes, you'll see that there's an infinite number of different size infinities of ever greater sizes. And that's really fascinating. So what we've done here, this concludes our application of logic to set theory in mathematics. We've shown you how the materials that you learn in this class are actually the basis for exploring and proving a lot of the fundamental truths of contemporary math. Okay, thanks.